Good morning and welcome to today's Electronic Design webcast. Our topic today, understanding and solving thermal design issues in MOSFET applications, sponsored by TTI and Nexperia. I'm Bill Wong, Senior Content Director with Endeavor's Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, just type your issue into the Ask a Question box and a member of our team will assist you. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send your questions at any time. To do so, simply type your questions into the question or the Ask a Question box and click on the Send button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Tom Wolf is a Technical Applications Manager for Nexperia. Tom has designed automation systems for IBM and GE and provided application design engineering for semiconductor manufacturers Intel, AMD, NEC, and Philips, now NXP. Now let me turn things over to our presenter. Tom, the floor is yours.
Thank you, and welcome to our training module on understanding and solving thermal design issues in MOSFET applications. I'm going to give you a hint right off the top. Whenever you're working with MOSFETs, it's always about the heat. If you can control the heat, you will do amazing things with MOSFETs. Incredible currents, wattage, voltage, amazing things if you control the heat. So that's really the purpose of this presentation then, to understand those thermal issues, how to design around them, and how to overcome those issues, which inevitably are going to come up during your design. So here's what we'll do. We're going to learn how to understand the requirements of an application on MOSFETs. We could talk theoretically, but it really works better if we use an exact application. So I've picked one here, brushless DC motor control, as used like in power tools and vacuum cleaners and things like that. It's very common, but it allows you to see in a real world example how all these thermal things work. So we'll talk about that, but of course, these theory apply to any application where you're using MOSFETs, of course. I want to show you how to use the datasheet to parameters to select the correct MOSFET. Obviously, if you start with the wrong one, you're going to end up with a horrible thermal solution. So it starts at the beginning. Pick the right part, gets you a good way along to coming up with the right thermal design. Then this next section is relatively new. We want to show you how to simulate this thermal design with common software tools. And these are not the real exotic stuff that we can't afford a license for. These are tools that you can download for free and run them yourselves and get a really good idea of how your system is going to perform before you buy the first MOSFET, before you put the first piece of solder on the board. So it's a really important tool for understanding if you pick the right part. You're going to simulate it. And then the final section is I want to show you how to configure the PCB in the entire system, the heat sink, the cooling, however you're going to build this system for optimum thermal dissipation, because again, it's all about the heat. So these three stages should allow you to pick the right part, design it properly, simulate it, know if it's going to work, and then how to actually lay it out on a system so that the whole system works the way that you intended. With that, let's get started with our first application. And to do that, we need to understand a little bit about the fundamentals of motors. That's what we're going to try to drive in this application, so we need to know a little bit about the basics of them. In the past, a matter of fact, almost 200 years ago now, the first motors were designed. The first brushed DC motor applications and AC motors were designed. And they've stayed that same way for, like I said, almost 200 years. They're all fundamentally the same thing. You have a rotor, the part that spins in the middle that does the mechanical, does actually the mechanical work on it. And then on the outside of it is a permanent magnet. So magnetics on the outside, and then you have an electromagnet on the inside of it on the rotor, which changes its electromagnetic field to repel or attract against the fixed permanent magnet on the outside. The way it does that is through something called the commutator, which has brushes on it. Hence the name, it is a brushed DC motor. As the motor turns, the brushes select different parts of the commutator and turn on different magnets on the spinning electromagnetic section, which react with a permanent magnet and the motor turns. Again, this has been going for almost 200 years. Very common, applications are everywhere. The new thing though is all new applications are switching to something called a brushless DC motor. And here they are. And you can clearly see there are no brushes on it. There's no commutator because the entire motor has been turned inside out. Instead of having the permanent magnet on the outside and the electromagnet on the inside, it's the other way around. Permanent magnet is what spins, and the actual electromagnet is on the outside of it. Well, what does that mean? First, I don't have brushes on it, so I'm not limited by the mechanical switching speed of the brushes. The arcing and the wearing out and the carbon dusting and everything that happens with those, they're gone. Also, I don't have all those wires spinning around here, so I can spin a solid chunk of magnetic material really fast. So I can get a lot of speed out of this. It's not going to arc. It's way more efficient. Per pound, I can get way more power out of one of these motors than I could the original electromagnet spinning type motors, the brush motors. The complexity, though, is that now that there's no commutator, how do I know what magnet to turn on, electromagnet to turn on to make it spin in the right direction? Well, the electromagnets are on the outside. I can hook circuitry directly to them. I don't have any rotating contacts for it. So I can now determine when I want to turn these electromagnets on the outside. The faster I can turn these magnets, moving one to the next around it, the faster I can spin the permanent magnet inside, and the more control I have. One of the marketing buzzwords for these is digital motors, not because they're really digital, but because digitally I control how the electromagnetic field changes, which makes the motor go. All new applications are using these. All the new appliances, white goods, power tools, automotive applications, everybody's moving towards brushless DC motors because you have way more control over the mechanics of the system. The reason we like them so much is this digital section. It requires a lot of electronics, a lot of power electronics, and in particular, power MOSFETs, and that's what we're talking about today. So the fundamental example, a brushless DC motor then, like I said, it looks like a permanent magnet spinning inside an electromagnetic field. And to make it operate, all I need to do is put energy to each one of these electromagnets in sequence. The permanent magnet inside will follow them and then turn. So here's the animation of it. As you can see, my north and south poles reflected by the red and the black. All I need to do is keep moving the field ahead of it so that I'm constantly attracting the motor to the next section. If I want to reverse it, I can do the same thing. I can reverse the field, the pattern of the field on the outside. The motor turns the other direction. I can make it go faster. I can make it go slower. I can do all kinds of amazing things, all based on my software. It's no longer fixed on the commutator, the fixed mechanical structure of the motor. It's now all digitally controllable by a CPU. The motor will do whatever I tell it to do within its laws of physics, which are pretty impressive. How do I hook them up? Here's the wiring inside the device. It just looks a little complex, but it really isn't. Inside the motor, I've got the spinning permanent magnet with its north and south pole on it. Here's the coils around the outside. What I want to do is I want to make each one of these coils in turn go from off or from north and south to south and north. And then I just simply walk that pattern around. The way I do that is I don't have to put separate control on each one of these magnets. What I do is I connect every third one together in this Y configuration. So this would be my first set of coils, my second set of coils, my third set of coils. I don't have to have just 6. This is a simple example. I typically have multiples of 3. I can have 6 or 12 or 24 or 36 or any multiple of 3. The steps just become that much smaller, but they're all hooked up the same way. So to make this operate then, as shown on the diagram on the left, all I need to do is energize one of those 3 sets of coils. They switch from north to south and south-north. The magnet inside spins to that condition. I then know where the motor rotor has turned to, and I can say, now it's time to go to the next one. And then I turn on the next set of coils. So literally, I am leading the electromagnetic field around the permanent motor and pulling it into position as I go. That, in essence, is 3-phase basic operation of a brushless DC motor design. So how do I control these 3 coils, these 3 sets of coils? How do I control them in the right stage? That's where the MOSFETs come in. So here's a typical control schematic of a system. This would be a brushless DC design, and they're almost always made up of 6 MOSFETs in the phase controller itself. Each phase, here's that phase that we just showed before of the 3 different connections in it. Each one of those has 2 MOSFETs assigned to it. One which is connected to the VCC, the battery supply, the plus supply, one which is connected to the negative supply. So by manipulating the high side versus the low side FET, I can turn them on so that I get a north and south pole, or I can reverse these so I get a south and a north pole. I can flip the polarity of each one of these 3 magnets independently by use of these 6 MOSFETs. So all I need is some sort of microprocessor or timing circuit to say, hey, high side FET for the U phase, you turn on now. By the way, turn off this one at the same time. And then as I sequence through them, I can cause these electromagnetic fields to rotate from one position to the next, and then the motor will follow it the same way. So that's fundamentally it. And this is why we're talking about MOSFETs. Every design has at least 6 MOSFETs in it. How do I pick those? How do I control them? Let's look at that next. So brushless DC motor control. The MOSFET on board, these are the requirements that it needs. The motor windings are always connected to something. You're either positively charged in a north-south configuration or your reverse polarity to a south-north configuration. You're always turning them back and forth. Those magnets are constantly flipping back and forth, so there's always some current applied to it. There is something called repetitive avalanche we need to worry about. We're not going to deal with it too much in this presentation, but avalanche is the condition where the drain and the source of the MOSFET itself are reversed. In other words, you put opposite voltage on it, your MOSFET must survive it. You're trying to force electricity backwards through the MOSFET. So you must have a device which can tolerate that. In general, motor applications switch on the order of 10 to 20 kilohertz. I know that sounds fast, but it's not. Power supplies work in the megahertz. They're much, much faster than that. So in reality, 10 to 20 kilohertz is not that fast. It's not that hard to find a MOSFET that can switch at these speeds. I need to pick a MOSFET which is rated for the voltage I want to run. Since we're talking about battery-powered applications, 5 cells, 5 lithium-ion or lithium polymer cells. They will give you 18 volts nominal, 15 to 21 volts, depending on whether they're charged or discharged. So if I have a maximum of 21 volts, I need at least 21 volts for my MOSFET. 30 volts seem to be ideal. That gives me a little bit of headroom. If you're working in a real noisy environment, maybe you pick a 40-volt MOSFET. But the voltage of your battery determines the size, the voltage rating of the MOSFET that you need to have. For motor controls, low RDS on is always key. It's a chase to the bottom now. How low of RDS on can you do? The best parts are now on the order of 1/2 of 1,000th of an ohm, 0.5 milliohms. And that's still not low enough. That's continue a chase to get to 0 in theory someday. Of course, you'll never get that low. But you want the lowest RDS on because that is the resistance through the MOSFET. I don't want to turn heat. I don't want to turn my current into heat. I want to turn into energy. So the lower resistance, the less current, the less wattage and heat I have to deal with in the first place. I need to have high current capability to cope with things like rotor stall currents. You know, when you're using a tool and it hits a knot or hits something hard in the concrete and the rotor locks up, your current can go to hundreds of amps in a millisecond. And you need to be able to tolerate that or you're going to blow your MOSFETs up. You need a certain amount of time to tolerate that before the part actually stops working. And then finally, I need something like soft switching, which is required for good electromagnetic control. I do not want this thing to make so much noise that it shuts down all the radio and TV in the area when it's running. So these are kind of the requirements. When I'm building a brushless DC motor, this is what I'm going to ask of the MOSFET. So let's look at each one of them then. The breakdown voltage is called the VDS, voltage drain to source, because battery voltages are going higher. Every new generation, you need to come up with higher MOSFETs and higher voltage batteries. 30 and 40 volt MOSFETs are the mainstream today. We're now looking at 60 volt battery applications like lawnmowers and things like that, which will require 100 MOSFETs for the heavy duty tools. And I guarantee these requirements are going to just continue increasing. Every new generation, there's going to be a new requirement for a new MOSFET. The maximum current rating. This is the maximum amount of current you can put through the device. And again, you need this for the fault condition. The rotor locks because you hit something hard in whatever you're drilling or cutting through. So I need to be able to tolerate much more than my static condition. Remember that a MOSFET must be able to survive until your overcurrent protection tips in, which may take a couple milliseconds. So I need to be able to tolerate that massive current rush before my microprocessor says something's stuck, turn the whole thing off and disconnect it. And then finally, I need good thermal performance. I need low R Thevenin. I need to have the lowest thermal resistance possible so that the heat can come out of the junction, out of the inside of the package as quickly as possible so that I can perform at higher temperatures without melting the part up. The higher maximum junction temperature I have on board is at 150 degrees C, 175 degrees C. The higher that is, the more heat I can pump into it before it becomes a problem. And then finally, I want the lowest RDS on I can get just to manage the temperature. I want to make sure that I'm not creating heat in the MOSFET that I have to get rid of as well. I'm losing efficiency and I'm creating heat that's going to make my thermal solution that much more difficult. From a gate drive point of view, what is the signal which turns the MOSFET off and on? Well, I can select either a logic level device, which runs 0 to 4.5 volts for off and on for the gate. That's useful if I have low battery voltage. I can still control it even if my batteries are nearly dead. But I might want to pick a part which is a standard level, which operates at 10 volts. That gives me immunity to false turn-ons. A noise pulse of 5 volts doesn't turn the MOSFET on. I need 10 to turn it off or on. 10 volts seem to be the biggest standard, by the way, right now, but either one depends on your design. One thing you do need to remember, though, is that gate threshold, does it turn on at 2.5 volts or whatever it is? That changes both with age and with temperature. So I need to be aware that my circuit must compensate. As the part gets hotter and gets older, that turn-on voltage may switch as well, too. I need to look at the safe operating area of a device. This is how much current can it do for how long? How many amps for 1 millisecond? How many amps for 1 microsecond? It's a whole chart of values which lets me know how long I can stay in a particular power mode for a particular device. I do need to remember that in some cases, the collapsing battery voltage means that the gate might not be turned on. The more voltage I put on the gate, the more the MOSFET turns on and the lower RDS on, the lower resistance through it. As my battery gets weaker, my RDS on is going to go up because I'm not turning it on as hard as I used to. So I need to compensate for that. And then finally, size. I want to put these MOSFETs as small as I can. The common standard today is a 5x6 millimeter package. Hold up your hand and look at your fingernail. Your pinky's probably on the order of 5x6 millimeters. We're talking very tiny parts. There's also 3x3s available, 8x8s, and heck, there's even 2x2s and 1x1 millimeter packages. But it all depends. What are you driving? How much space do you have? That's the package that you're allowed to pick. And of course, that's going to set the thermal resistance and the RDS on of the part as well, too. Final one is the Avalanche Rating. This is the application where the drain voltage exceeds the source. The voltage is backwards on it. This is something that always happens with magnetics. When I put energy into a magnet, it creates a magnetic field. When I disconnect the electricity, that magnetic field turns back into electricity, which goes straight back into the MOSFET. So my MOSFET needs to be able to tolerate that voltage forced into it during that application. So I want a high Avalanche Rating. The difficulty is there's not really standards for that. So I know I need a good one, but how good? A little tough to measure sometimes. And then finally, the spike control. This is for FCC certifications. Again, I may need to put snubbers on it. I need to deal with the reverse recovery. This is the amount of noise that this circuit makes when it's actually turning off and on. A cheap or poorly designed circuit will actually physically make sound. You could physically hear it running when the MOSFET drivers are turning it off and on. A good one will be dead quiet. So it depends what your application needs. So let's look at the part numbers. The MOSFETs then, depending on the number of cells that's in your battery pack, anywhere from 1 to 10, we can actually pick apart. We know what the nominal voltage is, the maximum voltage. Based on that, then we can pick a particular part number, which will give me the RDS on, the voltage that I need, the avalanche protection will be built on board, how many amps I can handle for it. So use this as a rough guide. If you're working with a 5 battery cell tool, you know that I'm probably going to be looking at these particular devices are the ideal parts to start with for your design. So we've looked at what are the parameters which are required to actually design the MOSFET board in the first place, the control for the BLDC. How do we know if it's going to work? Or more importantly, will it burn up? Before we put anything on the board, let's do some simulations. And the good news is there's tremendous applications available nowadays that allow you to do this simulation with a minimal amount of tools. Now, why are we doing thermal analysis? Remember, MOSFETs are all about the heat. If you can remove the heat, you can put more current through it. So it's always about getting rid of that heat, not generating it in the first place. And then if I do generate it, getting it from inside the package to outside to my heat sink or fan or water cooler, whatever it is, as quickly as possible. Power flowing through a semiconductor always generates heat. More power, more heat. I need to flow away from the device to keep it from blowing up. Not only that, but it will also cause reliability issues. Even if the part doesn't physically explode, running it past its maximum junction temperature, 150 to 175 degrees C, is going to impact its life. It can only do so many million switches or billion switches, depending on what that temperature is, and you will shorten its life if you're running it outside its operating range. So thermal analysis allows you to understand what your application is going to do to the MOSFET. Again, think back to the power tool application. When you use a power drill, how often do you normally turn it on? Well, it's not on 24 hours a day. It runs for a few seconds at incredible loads, and then it turns off and it has a period to cool. So that is the use of that application, and every application is going to have different use for it. So once you understand how long I have to drive so much current and how much time I have to cool it down, now it's possible that you can actually simulate that environment and understand how your design is going to work before you actually build it. So there's two primary ways of doing thermal modeling. The first one is the fancy way. If you have access to finite elemental analysis, wonderful. Use that. But it is a expensive tool. Licenses are hard to find for it. Costs a lot of money. Good learning curve for it, but it's really good when you get done for it. The example that Nexperia uses internally for our model simulation is flow therm model. However, most of us don't have the luxury of that. I don't have the luxury of it. So what we want to work with is something called RC for resistor capacitor modeling, where we use something called thermal electrical analogies, and it runs under a SPICE package. I think everybody knows that you can get LTSpice for free. You can download it off the web. The variables for the Foster models or the Cower models, which is what these RC models are called, are available free from our website. So literally for no cost, you can build a pretty good simulation in SPICE or LTSpice and determine how your system is going to operate before you solder the first part on the board. So let's compare those two then. Finite element analysis, it is the best. I got to admit that. It takes a while to learn it. It's relatively expensive and the complexity, but it's really good. Matter of fact, I'll show you some examples at the end of this presentation, which were done on flow therm. You get some really neat thermal maps off of it. RC modeling though, hey, you know, it's pretty good. The accuracy is as good as our model. We put a lot of energy into those, so they're really good. It's quick. I'm going to show you in 5 minutes how to build your first model and actually run it. It's free and it's relatively simple to put them together. So hopefully, if nothing else after this presentation, you have the ambition to go out and actually build one of these models using Foster or Cower models and actually try it out yourself. So let's get started then. RC models use resistors and capacitors to represent the thermal values, the wattage and the current, which is flowing through the motor. Basically, because it turns out from the laws of physics, they're very similar to each other. We all know about Ohm's law, R equals V equals IR, or R equals V over I. We use that all the time for resistors, current, and voltage, very easy. Turns out there's a thermal model as well, too, that there is the resistance, which is K divided by watts, Kelvin divided by watts. So I can actually do a similar calculation thermally that I could do electrically. Well, these two relate directly to each other. In Kelvin per watts is the thermal resistance. RTH is a thermal resistance. It is exactly equivalent to electrical resistance. It is the inability for something to, it's the ability of something to stop allowing voltage to flow through something, it's a resistor, or to stop letting heat flow through something. Both of them are resistances. I have a temperature resistance, which is exactly matched to potential difference, which is what we call voltage. I have dissipated power measured in watts is an analogy to current, which is measured in amps. And then I have thermal mass. This is the ability of something to store up heat and then cool down over a certain period of time, like an insulator versus a thermal conductor. And that is an analogy to the electrical capacitor. So I know a whole bunch about these, how to use Ohm's law and the simulators, and LTSpice is based on those. If I can figure out the equivalent of the thermal values to the electrical values, I can use electrical tools I already know to do real thermal analysis of the system. So thermal resistance, again, from an electrical point of view, I can actually measure the resistance. It's the voltage difference from the input to the output of the resistor, measured by the current. We all know that one. Well, it turns out thermal is exactly the same too. The thermal resistance is equal to the temperature on one side and the temperature on the other side of the material itself, divided by the heat flux, which is measured in watts. Heat flux is like current. So a direct analogy. I really don't have to do anything between the two. They are one-for-one comparisons, electrical versus thermal resistance. Same thing for capacitance. This is the ability of an item to hold heat. Once I heat it up, how long does it take to cool down? Just like a capacitor, I put voltage into it. How long does it take for the voltage to discharge from the device? Well, heat's exactly the same way, and actually do a direct comparison for those. So I can take a part that Nexperia builds one of our MOSFET devices, and I can actually calculate the equivalent thermal resistance and capacitive capability of the device, the thermal capacity of the device as well too, convert those into R's and C's, run them on SPICE, and I can actually simulate the thermal with electrical equivalents that, again, we all know. So this is what it looks like. Inside the device itself is called the Foster model part of it. These are available on our data sheet or on our website. All I need to do is plug in these values of R and C into my SPICE model, and it will calculate, instead of voltage and amps, it will actually calculate heat, watts, and temperature instead. If I'm lucky, and I know the Cower models of all of my PCB, of my heatsink, of my printed circuit board, of my thermal vias, I can actually connect the two together, and I can simulate the heat from the junction of my MOSFET through the package, outside of the Nexperia device, onto the solder, onto the PCB, through the vias, out to the heatsink, out to the airflow, out to the liquid cool, I can actually simulate an entire environment using just LTSpice. That is one impressive tool that is now available. Like I said, we'll provide the Foster models from Nexperia directly, the Cower models for our parts, and then you can also get Cower models from your heatsink supplier or your solder supplier. They have those values as well too. So let's look how we would actually do a simulation. Now, to build these models, what we do is we take something called the thermal impedance curve, the ZTH, curves for a device, which is what we actually measure. We design to this curve. It's in our data sheets, no surprise there. You can actually build that curve based up on a series of RC curves. Simple geometry here, simple creating equation matching, that I can build this actual physical curve with a series of other small RC curves. If I then take these R and C curves, I can then create them in a model, and now I have a thermal equivalent of the actual measured curve of the device that I can now turn into volts and amps and plug into my simulation. So we do this part for you. This is all created. You just go and download RC values for these multiple pairs. Each of these pairs then goes together and creates the entire simulation model. The advantage of RC models versus using that thermal impedance graph, however, the impedance graph in our data sheet is really useful for simple square pulses. I'm just going to turn it off and on. It's very easy to simulate it. I can just do a little math because it's the area under the curve. However, if I get to really complex applications where I have sine waves and various duty cycles and things like that, it becomes very difficult or very tedious to calculate each part of the curve and add them all together. SPICE does that for us, though. All I need to do is input my complex wave shape based on my actual user application, and then when I'm finished with that, it will tell me what the output, what the performance of that equation is. So again, I can do thermal modeling with just equations and paper and pencil, but a SPICE model automates it and does it all for me. So this is the example where it's really useful to have a simulation model like this. So we've talked about it enough in theory, really nice. How about if we actually go and create a real world example for it using a particular part in a particular application? So to set one up, go get LTSpice, download it for free on the web, go to the Nexperia website and download the RC, the Foster models, which are available on our website. This is one of our parts of UK9Y19. Go down and you actually see here are the thermal models. They're on our webpage. You download them. You create the model in SPICE. I'll show you on the next page how it's done. Now remember, temperature equals voltage. So I want to start one side of my thermal solution is my starting voltage, my starting temperature. So I put in 25 degrees C, that's 25 volts. I put that in, I measure the maximum temperature on the other side of it as well too. For example, if my part can only run to 150 degrees C, I know that the voltage on one side is 150, the voltage on the other is my starting voltage of 25. How does that voltage, how does that heat transfer across the device? And I can create all kinds of current sources for it. I'll start with the simple one, but you can make them as complex as you like and build them. Once I've got these pieces together, I'm ready to go into LTSpice and actually create the model. And this is what it looks like. This is LTSpice. I took the model. These were directly taken from our website. You don't have to do anything fancy. All you have to do is draw a bunch of R's and C's. You plug in the values according to our data sheet itself, according to our table, and you create this simple structure. So I have a test point at the bottom. That is my starting voltage. My 25 degrees C is 25 volts. There's the RC networks that we give you. There's my current source, which is going to be how much power you're putting into this circuit. How many amps for how many seconds, and what is the duty cycle that you're going to pump into the circuit. And then I'm going to measure at this top point up here, what is actually the voltage of the system. The voltage will then tell me the temperature of my device under those specific operating conditions. So let's go ahead and set it up then. Again, we'll set 25 volts is the case temperature. That is the starting voltage temperature. So we put 25 volts into it. There it is at the bottom of the equation. I want to create a single pulse event. Like this is a fault condition, for example, where I want to calculate when in a certain amount of heat goes into the part, how fast does the junction temperature rise? Because remember our mantra here, if I can control the heat, if I can keep it within the limits of the junction temperature of the part, my circuit will work. If I go outside that, the part goes boom. So I want to measure my temperature. I want to simulate my temperature inside the part based on my particular conditions. The current source that's in the model will represent the power the device is absorbing. And again, you can either just put in simple square waves. There's a bunch of tools in LTSpice for creating sine waves and square waves and triangles. And you can even use Excel and create a very unusual waveform, a dot at a time. You take Excel and create it. Again, that's beyond the ability of this course, but it basically means that you can create any wave shape and feed it into my circuit, which again is a voltage circuit, but it is actually telling me the junction temperature of my semiconductor device, which is what I'm worried about. So here's the example then. I'm going to use the Buck 9Y19-55B, just randomly picked there. I want to see how it actually operates. I want to put the current into the part which is a repeating pulse. That's the most common. I hit it with square waves. I put a bunch of energy into it. I turn it off. I let it cool down. Hit it with another pulse. Let it cool. It's typical. I control those electromagnets on my brushless DC motor design. So in this case, I want to set a period of 20 milliseconds, 50% duty cycle, peak current of 50 amps. So I'm going to hit it for 50 amps for 10 milliseconds, turn it off, let it cool for 10 milliseconds. Then I'm going to hit it again because it's 50% duty cycle. And I want to look at it for 200 milliseconds because after 200 milliseconds, I know my microprocessor will measure the temperature in reality and go, too hot, shut everything off. So I have a 200 millisecond window I need to tolerate with this particular system. And here it is. So this is my input current. This is my starting voltage. This is the RC that I've created from it. And then this is actually the wave shape of the part itself so I can test various parts inside the simulation. This is a SPICE model. I'm not measuring the actual response, the analog response to it. That's a true SPICE model. This is a voltage simulation of a thermal model using SPICE instead. So let's see what happens. Here it is then. The blue is telling me the pulse. So like I said, I hit it for 50 amps for 10 milliseconds. Then I turn it off. I turn it on again for 10 milliseconds and I turn it off. The green line is actually the temperature. I'm measuring the voltage, but it's actually the temperature of the junction of that MOSFET because every time I hit it with current, it heats up. Then when I turn off the current, it cools down a little bit. Then it heats up again and it cools. Notice the trend though. It doesn't have enough time in 10 milliseconds to cool all the way back to zero. So I'm constantly adding heat onto the system. So I know that at this rate, it's either going to go off the chart, I'm going to exceed my maximum junction temperature and destroy the part, or it's going to stabilize. This particular example, because once I get enough thermal mass, enough thermal capacity, the part begins to then pass the heat out of the heat plate into the circuit board. The circuit board can then be a massive heat sink and it can pull it off. So in this particular simulation, I'm going to max out at about 130 degrees C. In other words, it's a good design. I know that at the beginning, it's going to heat up rapidly. Once it's heated up to a certain point though, that part will not get much hotter. It never goes to that, 150 up here, 175 degree under these conditions. It's a good application. I can get the heat out of the part under the operating conditions that I have. And I can change this all I want. That's the nicest part about this tool. So I've done it for just a 50% duty cycle here. Well, what's going to happen if I increase the duty cycle? What if I decrease it? What if the current goes way up for shorter periods of time? I can actually calculate that and play with hundreds of examples before I ever solder a part onto the circuit board. So summary for it. RC thermal models represent the thermal impedance curve, which is in the data sheet. Using those RCs, you can then simulate how the part is going to perform for your specific case use. The current, the power going into the device, times the amount of time, it will then tell you how hot is the part going to get inside. These thermal models are available on our website. Like I said, go download them. Virtually every part, every MOSFET we have has that model available, so you're ready to work with that. In the SPICE simulator, you just go ahead and set it up, as we've shown you with RC equivalents. If you want to get fancy on it, you can also add in the gate voltage and the gate current, because that actually is pumping energy into it. That gate control adds a bit more power into the MOSFET. So if you really want to know everything, you might want to add that in. In most cases, it's insignificant, but it's an option that you might want to put into it. And do remember, and the SPICE model takes us into allocation for normal operating. In the real world, the parameters like RDS on change as power goes through the MOSFET. RDS on gets higher the hotter the part gets. So I need to compensate for that. SPICE can do it in the middle of the curve. If you start getting out near the edges of destruction, you need to be very careful is that my own self-heating, because the RDS on has gone up, is now modifying my equations. But again, that occurs out of the edges. There is new modeling work coming out, which someday we'll be able to compensate for that as well too. But just for brute force simulation, you can always take just the simple tool which is available, and then based on that, you're ready to go out and do a simulation of your system before you actually build it. So we've got the heat created inside the MOSFET itself based on a particular application. We have now simulated the model so that we know how to get the heat from the junction inside the MOSFET out to the outside of the part. So we're now at the mounting point, the place where the drain actually connects onto my PCB. How do I design my PCB to get the head away from it? Now, this is something that Nexperia, we don't build PCBs, but we know you're taking our device and putting them onto the circuit board. So we want to make sure that you understand the goals and the methods of getting the heat out of our part through your circuit board and out to your heat sink or whatever your final thermal solution is a system. So let's take a quick look at the PCB design concepts, or better yet, what to do right and what to avoid doing wrong when you're laying out a PCB for your power MOSFET. Remember what LFPAC is. It is different than pretty much every other MOSFET in the marketplace because it uses what we call a copper clip technology. You can see in this cutaway diagram, this is of the LFPAC 56. On the bottom, I have this gold plate. That is the drain connection. That is the big heat pad on the back of the package. I solder that right down onto my circuit board. So it's the primary way that I get heat away from the junction, away from the piece of silicon, down into my system to cooling. Now, most manufacturers of MOSFETs, that's all they got. They don't have the second clip on the top, which Nexperia has. We add a copper clip on the top of the silicon as well, too. It's the source clip where the voltage goes in. This source clip then is thermally connected. It's one piece of copper from what's on top the die, straight out through the junction, right down to the pins. Now I can take these three pins, these three source pins. If I put thermal vias under those, I can put heat from the source down through the bottom of the board as well too. So this gives me thermal solutions from both sides of the piece of the silicon. Other vendors have to call this top side cooling or dual side cooling. We've always had dual side cooling. Approximately 60 to 70% of the junction heat goes out of the drain side. The other 30 to 40% actually comes out of the top of the part, and I can then route it down into the board. So I can put 100% of my heat down through the PCB to my heat sink or chassis, which is on the other side of the printed circuit board. So I don't need topside cooling. In fact, you could try to clip a heat sink on the top of the plastic package. It really doesn't add much in particular because we've already designed it for the optimal thermal solution using the part. So based on this, you want to design the thermal solution for a Nexperia flat pack differently than you would design other MOSFETs. I don't have to worry about a heat sink on the top. I don't have to worry about double side cooling. I know that essentially 100% of my heat is going to go down onto the printed circuit board. What do I do with it once it gets there? So let's look at that then. The industry uses a standard 1 by 1 inch copper area, 25 by 25 millimeters, for all its thermal simulations. And you'll find this in all types of books. It's an industry standard. JEDEC hasn't accepted it, but it's actually out there already. Let's take a common example then. We're going to take here's our 1 by 1 inch piece of copper. We're now going to solder the MOSFET onto it so we catch all the drain, because remember, that's the big pad on the back of it. But remember, for a Nexperia part, I can also get heat out of the source pins as well too. So I want to put some copper under the source pins to actually take that top side heat down through the board as well too. Let's assume for our base model then that the PCB is single-sided. It's standard FR4 material, which is kind of a vague term because copper thickness may or may not be specified in a common model. The maximum temperature and voltages and power dissipation may or may not be in the standard model for it. But it gives me a starting point for what is a system going to do when I take my MOSFET and I solder it onto a printed circuit board. And in this case, I'm using a different MOSFET just because the way the math worked out here. PSMN happens to be a 1.0 milliohm, 30 volt N-channel MOSFET in our commercial line. So let's see what happens when we actually put heat into this part. How does the PCB respond to this condition? Remember I told you before I was going to show you some flow therm models? Here they are. This is the pretty pictures you get out of the real high-end thermal simulation models, all nice colors and everything. It shows you where the heat is. So for the first example where I'm taking my 25 by 25 inch model space, I'm going to use 4-to-1 ratio, 4 units of copper under the source to 1 unit of copper under the drain to 1 unit of material underneath the source. What does the model look like? So I can actually build this, I can simulate it in flow therm, or I can actually construct it. In a 20-degree ambient temperature and 0.5 watts of power dissipation, my junction temperature goes to 53.1 degrees C. Good starting point. And by the way, it's really good because my junction can go to 150. I got plenty of extra room under my test conditions for this particular printed circuit board layout. And that gives me a theta JA, that's the junction to ambient thermal resistance of about 66.2 kilowatts, K per watt. So that's a pretty good number, but there's better numbers available. So if I start changing around the ratio of copper I put under the drain versus what I put under the source, what happens to it then? Well, let's run another simulation for it. Here it is 3-2. I put less of my material under the drain on the PCB. I've put more of it under the source. You know, wait a minute, I thought most of the heat comes out of the drain. Yeah, but a lot comes out of the source. I run the simulation again. Junction temperature now is 52.7. I've dropped a degree or so off of it. In other words, adding more material under the source, which wouldn't work at all for other manufacturers' MOSFET, cools our junction temperature down. I'm getting more heat out of the source just by changing my printed circuit board design. Also notice that the theta JA has now gone to 65.4. I'm getting closer to the mathematical ideal. If I can keep pushing that number, I will have the maximum efficiency, which allows me to put more power into the MOSFET without overheating the junction, because I have a good way for the heat to flow out of the MOSFET package into the circuit board itself and then dissipated safely away. So a conclusion for that. Let's look at it then, kind of in general terms, is that I typically want the device somewhere near the center of the copper area. I want to put most of the copper on the drain, but I do want to put copper under the source as well too. And also, if I inset and bring the curve around the side, I didn't show you the actual model for this, but it turns out is if you allow the heat to flow out essentially as much as 360 degrees around the device as you can, that gives me more cooling area as well too. Other things I might do, we didn't talk about this in the model, but I might want to increase the copper thickness to put more copper on it. I might want to use high conductivity FR4 material, the epoxy board itself. I want it to flow more heat from the top side of the board to the bottom on it. What it comes down to is that if I keep working on the layout, I can get my theta JA pretty close to about 36 K per watt. The maximum mathematically calculable value is 34.9, so I'm getting pretty close to perfect there. By the way, if you start putting multiple layers of thermal vias underneath it and then spread the heat out even farther across the board through inner layers and through layers on the other side of the board, I can get even better. So again, this allows you the tool. Once I've created the heat in my MOSFET, by playing around with the board itself and how much copper I put under the drain, how much I put under the source, the geometrical configuration of the sink itself, the thickness of the board, by changing all these variables, I can possibly achieve that perfect number and get the maximum amount of heat out of the system, which means I can put the maximum amount of power into the front of it, and I can build the strongest brushless DC motor controller that I need for my application. So, summary, what have we learned in this? When you're picking a MOSFET for brushless DC motor design, the key thing to understand is what are you going to do to that MOSFET? How much power are you expecting it to be able to transfer through the device itself? How much current, for how long, and what are your tolerable temperatures? What's your starting temperature, and what is your final temperature, the maximum temperature before the part is destroyed? If you know those variables and you know how often your motor is going to be used, how long is it on? How long does it have to cool? How much current is it drawing? How much time do I need in an overcurrent situation before I must turn the device off? Once you know all those variables, you can now start building simulations to simulate those environments, calculate the amount of heat that's going to be created inside the device, and then based on that, I can go out to my thermal solution in my printed circuit board and design the optimal solution for it. Now, we've covered this relatively quickly. I have another resource available for you. You can download this directly from the Nexperia website, or you can pick it up in printed value as well, too. It's always nice to have paper for it. In this book, there's a whole section not only on how to do thermal models, more details on the RC, Foster, and Cower models. There's a whole section with more details on how to lay out the printed circuit board itself. In fact, I think you can say most of the information in this handbook is how to deal with thermal solutions, how to find those issues, and how to solve them for your next MOSFET design. So with that, that takes me to the end of my formal presentation here. I would love to open it up for questions. Thank you.
Great. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the Ask a Question box and hit the Send button. Also, please complete the feedback form when the webinar ends. So, to start with, what are the BUK part numbers compared to the PSMN MOSFET part numbers?
Okay. Thanks, Bill, for that question. We actually touched on that during the presentation. Some of the part numbers start with PSMN, some of them start with BUK. Silicon is the same. They're still essentially the same parts, same voltages, same RDS on. A BUK part is automotive qualified, Q101 qualified, so we give it a BUK number to identify that. PSMN is a commercial grade part, but other than that, they're both MOSFETs. The same rules apply to them, the same simulations apply. The book is accurate for both of them. It's just commercial versus automotive grade.
Okay. Does the application handbook get into the power RF applications?
RF, I assume, means radio frequency parts. These parts are not really designed for those very high frequencies. So no, not in particular. It's certain the handbook certainly does talk about the motor control frequencies, 20 to 30 kilohertz. It also deals with power supply applications, which are hundreds of kilohertz or up to a megahertz. RF, I would safely say, starts above that frequency, so probably not. So yeah, we can support up to the megahertz range with them, and that information is in the applications guide.
All right. Does your website have a typical power model for different reasonably common PCB structures? And also, how about the PCB effects, or how do the PCB affects the model, i.e. in thickness, layers, etc.?
Okay, what we're talking about here is Cower models. We spoke about Foster models and Cower models. The main difference between them is Foster is just inside the part itself. Cower allows you to expand your simulation outside of the device itself. I get the heat out of my part, now it goes into the PCB and the heat sink or whatever. Nexperia only builds the silicon. We don't build PCBs, we don't build heat sinks, but obviously we're familiar with them. So no, we do not have a particular manufacturer's PCB actual values for it. Go to their website and get the information from them. However, we do work with them on a common basis. So even in our applications handbook, we'll say, hey, assume the PCB is going to have these values. It's a starting point to allow you to at least work with some simulations without maybe knowing what the end result is. So yeah, some general terms you'll find in our application handbook. But if you're working with a specific heatsink, a specific PCB, please go to the manufacturer, that site, and get the exact numbers. Makes your simulation all that much better.
Okay. MOSFET capacitance, other than heavily nonlinear ones, introduce switching losses. The lower RDS on rating, the larger the capacitors or capacities. Is there a rule of thumb to optimize total losses?
That's a very good question. As you build lower RDSN parts, the way you get the resistance down is you make the die bigger. So because the bigger cross-section area, the more heat, the more current I can get through the device. So it reduces my resistance to the part. However, bigger dies have more capacitance to them. So I have to be careful when I switch them off and on. We're very familiar with this. When Nexperia designs the part, we actually use different silicon processing techniques to get lowest RDS on that we can, but also keep that charge down, keep that capacitance of the device as low as physically possible. We're using trench technology and some passivation and a number of techniques to get that down. But you're right, you need to be aware of that. The lower the RDS on, check the capacitance of the part itself. It's in the data sheet, and make sure you compensate for that. If you're turning on a large capacitance off and on rapidly, you're going to be losing energy just switching the capacitance off and on. So work with those. But those are all part of the model. So we do know those. They're in our regular SPICE model. That's the timing SPICE model. But also our thermal models compensate for that as well, too. Good rule of thumb, though, is that you want to get the lowest capacitance for the lowest RDSN part that we can make, and that's what we strive to do to make it easier for you to design those parts.
Okay. Driving the gate high is good for low RDS on. However, it reduces the MOSFET reliability by the increased risk of hot carrier trapping. Is the safe limit related to achieving the required RDS on?
Yes, hot carriers. This is the condition where when I'm sending current from my source to my drain through the part, through the channel, the part which switches off and on, you can actually get the energy carriers themselves, the energetic carriers can actually dissipate out into the gate. In other words, they leak out of the channel to get into the gate, and they can theoretically damage it over time. We are well aware of this condition. Because of that, turning the part fully on to 10 volts, for example, there's still headroom above that. In other words, we're aware of the hot carrier, and we make compensation for that in the design itself so that you are not impacting the reliability of the part by running it to its full specification. In other words, run it to the full 10 volts, still all the reliability fits for the part, all the reliability on TBF is in the data sheet. We still pass full automotive qual, full lifetime and everything for it. If you run above those levels, though, if you're running outside of our specification, above 10 volts, you can indeed get into that specification. But again, we are aware of that. It's impact reliability, and we use specific design techniques to make sure that hot carrier does not affect the reliability of these devices at the higher gate voltages.
Okay. IC manufacturers often provide application schematics where their devices drive external MOSFETs. We've seen circuits where the MOSFET is used in a DC linear application, but the chosen MOSFET is being operated outside the DC area in the SOA curve. How is this possible?
That may be a little more complex than we can deal here, but essentially you're talking about, I believe you're talking about the area when I'm turning a device from the off to the on state. I'm in the linear range between the two parts. Again, it is the silicon processing technique you use which tells you what is that SOA, how long can I stay in that linear mode. Very briefly, Nexperia uses a different physics, a different topology in our design. We use a superjunction structure instead of a split gate, which most of our competitors do. So we build parts with some of the widest SOA in the first place. So we're aware of that and have the ability to stay in that linear range for much longer than traditional designs. So hopefully I've answered that question. If not, please send it again and we'll make sure. It may take more than the time we have here to get into the details of that specific question.
All right. How do you take care of reverse voltage generated when solenoid is turned off?
Right. The reverse voltage you're talking about, and we mentioned in the presentation, is that when you put electricity into a magnet, you create a magnetic charge. When you turn off the electricity, magnet turns back into electricity, flows back into the MOSFET. Where's that energy go? Inside every MOSFET is a body diode. The body diode is fully rated for the same current and voltage of the switch itself. In other words, the MOSFET can absorb that energy safely. It's actually a very specific mode that we use. A number of automotive applications using fuel injection solenoids, for example, do not need a blocking diode on them. If you design the circuit correctly, you can actually use that body diode inside our MOSFET as the snubber to absorb that energy. If you do have a large amount of energy, our application guide shows you how to build snubbers to absorb that electrical energy if it's going to exceed or damage the MOSFET itself. But in most cases, you can design it so that the body diode already inside the MOSFET will absorb that energy coming back from your the magnetic collapse from the solenoid.
Okay. Is LTSpice thermal simulation of this type useful for MOSFETs used in their linear regions, like large electronic load applications? And do you have application guides for this type of usage?
Yes, the LTSpice model will work for that. The model we did was that we showed in the presentation was the 50% duty cycle off and on. You can extend those numbers to anything you like. Again, what you're doing is you're living in the linear mode operation of the device. You're taking a long time to turn it on, high currents for long periods of time, and the simulation will absolutely compensate for that. So you're right, you can indeed use our MOSFETs. Particularly the big ones, the LFPAC 88, the 8x8 millimeter packages, are built for those very high current applications that stay in the linear range for a long period of time. So yes, the LTSpice model will compensate for that. Our handbook does have some examples on how to use our parts in a more off-on as opposed to a PWM application. So again, look at the guide for that, and I think you'll find there are some solutions that let you run in that. We also have some new parts we're developing which have even more extended SOA operating range. Essentially, taking a MOSFET and increasing that linear range so wide is that you can basically treat it like a transistor. It becomes an analog MOSFET. So look at some of our newer parts, and you may find a part that fits that specific application.
Okay. Will Foster models run on the standard SPICE as well as the LTSpice tools?
Yes, correct. The Foster models are RC models, and so they will run on SPICE, which is the licensed version you have to buy. It's a little more elaborate, but it works on that. Of course, LTSpice is the free version you can download. It works equally well on that. Same model works on either tool. It's just, is it the commercial version or the free public version? That's all.
Okay. How can everybody get a copy of the MOSFET Applications Handbook?
You can download it right now. If you go to nexperia.com, type into the little search bar at the top, say MOSFET Application Handbook. It'll take you there. You can download the PDF immediately and start reading it right now. If you want a printed copy, which is great, my copies are all marked up and all kinds of footnotes in them. You can order one or contact your local salesperson, your local authorized distributor. They can get you a copy of it very quickly as well. Also, as a note, there's other handbooks too we didn't talk about here. The MOSFET handbook we did mention. There's a logic handbook in the series, tells you everything about our logic devices. Another on ESD design, electrostatic and TVS transient voltage suppression, and working one on bipolar. So eventually you'll be able to get a library of all of the wisdom of Nexperia in these books. But yeah, go online. You can download them right now if you like.
Okay. Do you have examples in the handbook for Class D amplifier designs?
Specifically Class D, no. A Class D amplifier, though, is essentially doing a lot of what a motor design is doing. Just you're modulating, you're changing the frequency of the PWM. Instead of always running it to 20, you're modifying it to put an audio signal through it. So a lot of the same information applies, but I don't believe there's anything in the book specifically on Class D amplifiers. We do have some articles. Go onto our website into the tech support section, the Technology Center, and take a look there. You'll see some basic information on them. We are indeed doing more work on that and actually looking at some parts really specified for Class D. So yeah, look there. If you don't find what you're looking for, hey, reach out to us at Nexperia, either myself, one of the FAEs, any of our sales team. We'd be happy to get you connected with one of our experts on Class D amplifiers.
Okay. Is there a top-side or dual-sided cool version of the LF pack available?
Not at this time. I mentioned it during the presentation itself, is that our part essentially is double-side cooled already. It's got a drain copper pad on the bottom of the package. It's got a source copper pad on the top, which then routes back down again. So there's no bare metal plate on the top where you would connect a heat sink. We've looked at it many times, done some actual lab work and measurements on it. There's a slight advantage to doing it, but the problem is now you have the mechanical issue of a large hunk of aluminum or copper sitting above the board. Your height restrictions have gone up. Does it really gain that much? So no, at this time there is not one. We certainly could build one. As a matter of fact, in our gallium nitride line, we have a dual side version of the LF pack that we use for those parts because they're extremely high voltage and current. So can we build one? Yes. Do we have one for silicon MOSFETs at this time? No, it doesn't really appear to have a good ROI to add that feature.
Okay. Does Nexperia correlate the thermal simulation results with actual lab measurements?
Oh, in other words, how good are the models? Yes, that's always an important thing. Remember that the models are created from the measurements of the device itself. They actually come from the thermal impedance models of the part. So when we build it, we actually test it. That creates then the RC curves, the many RC pieces, which build up the thermal model. So yes, the thermal model is created specifically from measurements of the device itself. However, we even test beyond that. Well, a number of times we've actually created simulations of a system, worked sometimes with a customer who then went on and built the board itself. Then we do lab measurements, actual thermal measurements of the board, and it is extremely close to the thermal simulation. So we have a very high level of confidence is what you see in the simulation model. If you put all the variables in, it will very closely reflect what you will get when you build a real system. So yes, we do indeed correlate them, and it's a pretty good simulator.
Excellent. Well, I'm afraid we've run out of time. For those questions that we didn't have a time to answer, we'll be getting back to you via email. This concludes today's presentation. On behalf of Electronic Design, I'd like to thank TTI and Nexperia for sponsoring today's event. Of course, to all of you for joining us. Have a great rest of the day.